Somewhere out there, right now, a star is dying. Not gently, not slowly, in any sense that would comfort us. It has been burning for millions of years, pouring light across an emptiness so vast that even that light grows old on its journey. And for all that time, it has looked eternal, unchanging, the kind of thing you could set your life by. But eternity, as it turns out, is only a matter of fuel. This is no ordinary star. Picture something thousands of times more massive than our own sun. A giant so heavy that its own weight is a kind of slow violence pressing inward at every moment. If you replace the sun with a star like this, our entire solar system would vanish inside it. The Earth, the orbit of Mars, perhaps even Jupiter, all swallowed, without effort, without notice. That is the scale we are dealing with. That is what is about to end. And here is the part that unsettles the mind. A star this large does not have the luxury of a long life. The bigger the star, the faster it burns. Our sun will shine steadily for roughly 10 billion years. A giant like this one measures its lifetime not in billions, but in a few short millions. A candle that blazes brilliantly, precisely because it is consuming itself so quickly. Its brightness is its doom. Its glory is the very thing counting it down. So when we look at it, we are looking at a clock. Every second, deep in its core, it is fusing lighter elements into heavier ones, extracting energy the only way stars know how. Hydrogen into helium, helium into carbon and oxygen. Each stage shorter than the last. Each stage a step closer to a wall it cannot climb. The star does not know this, but we do, and knowing it changes how we watch. There is something almost human in it, a life defined not by how it began, but by how it will end. For millions of years, this star has resisted the one force that has patiently waited for it since the moment it was born. And soon, cosmically soon, that resistance will break. What follows will be one of the most violent events the universe permits, and out of that violence, something impossible will be born. But to understand the death, you first have to understand the war. Because inside every star, including this one, a battle has been raging for its entire existence. A battle so precise that a single misstep ends everything. And that is exactly where we are going next. Look up at a star and it seems perfectly still, serene. But that stillness is a lie, or rather, it is the surface of one of the most balanced conflicts in all of nature. What you are actually seeing is a standoff. Two titanic forces locked against each other, so evenly matched that their struggle looks, from the outside, like peace. On one side is gravity. Gravity wants one thing and one thing only: to pull everything inward, to crush all that mass down toward the center. It never rests. It never weakens. From the instant a star forms out of a collapsing cloud of gas, gravity is already trying to collapse it further, to squeeze it down into a point. Left alone, gravity would win in minutes. But it is not left alone. Deep in the core, where temperatures climb into the tens of millions of degrees, something pushes back. Nuclear fusion. Atoms are slammed together so hard that they merge, and in merging, they release staggering amounts of energy. The same process that powers a hydrogen bomb, happening trillions upon trillions of times every second. That energy floods outward, and its pressure holds the star up against its own crushing weight. This is the war. Gravity crushing in, fusion pushing out. And here is the remarkable thing. For most of a star's life, the two are almost perfectly matched. Not because the universe is kind, but because the star self-corrects. Squeeze it a little and fusion burns hotter, pushing back harder. Let it expand and fusion cools, and gravity reels it back in. It is a balance that maintains itself. Astronomers call this state hydrostatic equilibrium, and it is the reason stars can shine, steady and reliable, for millions or billions of years. Think about what that means. Every star you have ever seen is not a peaceful thing at all. It is a controlled catastrophe, a bomb that is detonating so evenly it holds its own shape. The light that reaches your eyes at night is the visible proof of a war that has not yet been lost. And for as long as there is fuel to burn, the war stays balanced. But notice that word, fuel. The whole balance rests on it. Fusion only pushes back as long as there is something left to fuse. So what happens in the final moments, when the star reaches deep into its core and finds there is nothing left to burn? That is the moment gravity has been waiting for since the beginning of time. For millions of years, the star has been climbing a ladder. Hydrogen fused into helium, helium into carbon and oxygen. Then, as the core grew hotter and denser, heavier elements still, neon, magnesium, silicon. Each new fuel bought a little more time, a little more outward pressure to hold gravity at bay. But each step burned faster than the one before, and each brought the star closer to a rung it could not pass. That final rung is iron. When the core of a massive star fills with iron, everything changes, and it changes because of a hard, unbending fact of physics. Fusing elements lighter than iron releases energy. That is the whole business of a star, the entire source of its outward push. But iron is different. Iron is the ash of the cosmic fire. To fuse iron into anything heavier does not release energy, it consumes it. Consider what that means for a star that survives only by releasing energy. The core has been paying its bills for millions of years, generating enough outward pressure to match gravity's endless pull. And now, suddenly, the payments stop. Worse than stop, fusion of iron would actually steal energy away, draining the very support the star depends on. The account does not just empty, it goes into freefall. For the entire life of the star, gravity has pushed and been answered. Push and be pushed back. Push and be pushed back. Millions of years of perfect, self-correcting balance. And then, in the core, the answer simply does not come. Gravity pushes, and for the first time since the star was born, nothing pushes back. There is a silence to this moment that is hard to put into words. No explosion yet, no flash, just the quiet arrival of an imbalance that cannot be undone. The core has become a structure with nothing holding it up, a tower whose foundation has been pulled away in an instant. Everything that happens next follows from this single failure. The moment the long war was finally, irreversibly lost. And when a star this massive loses that war, it does not sag or settle, it falls. But the speed of that fall is something almost no human intuition is prepared for. Because what comes next happens not over years, not over hours, but in less time than it takes to draw a single breath. We need to slow down here, because nature will not. What happens now happens faster than thought, and if we do not deliberately stretch the moment out, we will miss the most astonishing part of the entire story. The instant the core can no longer support itself, gravity takes everything. The center of the star, an iron ball larger than our entire planet, collapses inward, and it does not drift inward gently. Material at the edge of the core plunges toward the center at speeds reaching roughly 70,000 kilometers per second. That is nearly a quarter of the speed of light. A structure wider than the Earth crumples to a fraction of its size in well under a second. Try to hold that in your mind, something the size of a world, falling in on itself so fast that if you blinked, it would already be over, many times over. The temperatures soar into the billions of degrees. The density becomes almost unthinkable, as matter is crushed into a space that should not be able to contain it. And still gravity pulls harder now, because the closer that mass packs together, the stronger its inward grip becomes. Collapse feeds collapse. Then, at the very center, something extraordinary happens. The infalling matter is crushed so violently that protons and electrons are forced to merge into neutrons. and the core becomes a single, unimaginably dense object, so rigid that the collapse slams to a sudden halt. The falling material hits this newborn core and rebounds, sending a shock wave tearing back outward through the star at colossal speed. So here is the strange truth of it. The most catastrophic inward collapse in nature does not end in a whimper. It ends in a bounce. All that inward violence is turned inside out, redirected back toward the surface, gathering the outer layers of the star and hurling them into space. The stage is set, the trigger has been pulled, and what happens in the sky above is about to become visible across the entire galaxy and far, far beyond it. Because when that shockwave reaches the surface, the dying star does something that defies belief. For a few brief days, this single point of light will outshine not thousands of stars, not millions, but entire galaxies at once. And we need to talk about how that is even possible. It is called a supernova, and of all the words in the language of astronomy, few carry more weight, because few events in the universe carry more power. When that rebounding shockwave finally blasts through the outer layers of the star and rips them into space, it releases an amount of energy that resists all comparison. Let us try anyway. In a single second, a supernova can release more energy than our sun will radiate across its entire 10 billion year lifetime. Read that again slowly. Everything the sun will ever give, every sunrise, every summer, every drop of warmth across billions of years, matched and exceeded by a dying star in one heartbeat. This is not brightness as we know it. This is the universe turning its volume to maximum. For a period of days to weeks, this one exploding star can shine as brightly as an entire galaxy of 100 billion stars combined. A single point outglowing 100 billion suns. There are supernovae so distant that their light has traveled for billions of years to reach our telescopes, and we can still see them because there is simply that much light to give. Astronomers have recorded these explosions in galaxies so far away they are barely more than smudges, and yet one dying star within them briefly rivals the whole. And yet, pause on the contrast. Moments ago, everything was collapsing inward, downward, toward a single crushed point. Now everything is flying outward, upward, scattered across light years of space, in and then out. The most inward event in nature immediately producing the most outward. It is as if the universe took the deepest breath imaginable and then exhaled a galaxy's worth of fire. There is a strange gift buried in this destruction too. The heavy elements forged in that final fury and in the explosion itself are flung out into the cosmos. The iron in your blood, the calcium in your bones, the gold anyone has ever worn, much of it was born in the death of stars like this one, scattered by supernovae across billions of years. We are, quite literally, made of the ashes of these explosions. But that is a story for another day. Because when the fireworks fade, our attention turns from the light to the dark. For all that outward glory, something stayed behind. At the very center where the collapse first halted, an object remains. It did not explode, it did not scatter. It sits there in the wreckage, silent and impossibly dense. And it is about to break the rules of physics themselves. The fireworks are over. The expanding shell of gas drifts outward, glowing, cooling, beginning its slow fade into the dark between the stars. And in the sudden quiet at the center of it all, we find what the whole story has been building toward. Something small, something still, something that should not be able to exist. Remember that rebounding core, the one so dense that the collapse smashed into it and bounced? For many stars, that core survives as a neutron star, an object with more mass than the sun, packed into a sphere you could drive across in a few minutes. A single spoonful of its material would weigh as much as a mountain. That alone should stop us cold. But for the most massive stars, even a neutron star is not the end. Even that unimaginable density is not enough to hold the line. Because when the leftover core is heavy enough, beyond a certain critical limit, nothing in the known universe can stop gravity from finishing what it started. Not the pressure between atoms, not the fierce resistance of neutrons packed shoulder to shoulder, nothing. Gravity, which pushed and pushed for the entire life of the star and was answered every time, finally meets a silence it can exploit fully. And it collapses the core further still, past the neutron star, past every barrier physics knows how to raise. Shift your thinking here, because we are leaving familiar ground. Up to now, every stage of this story has been something we can picture: a star, an explosion, a dense ball of matter. But what forms now is different in kind, not just in degree. It is not a smaller, denser object. It is a place where our very notion of object begins to fail. A region of space where gravity has become so overwhelming that it bends the rules we thought were unbreakable. This is the birth of a black hole. Not a thing sitting in space, but a wound in space itself. The star spent millions of years, an entire violent life, arriving at this single point. And that point, that place where matter has been crushed beyond all recognition, is where physics, as we understand it, begins to come apart. Which raises a question we cannot avoid asking. What actually happens to all that matter when there is nothing left to stop it from collapsing? Where does it go? The answer is one of the strangest ideas in all of science. A point where mass becomes infinite, size becomes zero, and the equations we trust simply stop giving answers. Follow the collapse all the way down. The core has already blown past every form of resistance nature can offer. There's nothing left to push back, no fusion, no atomic pressure, no packed neutrons. So gravity simply keeps pulling, and with nothing to stop it, the matter does not settle into some new, smaller ball. It keeps falling, inward and inward and inward. According to Einstein's theory of general relativity, the finest description of gravity we have ever produced, the collapse continues until the matter is crushed into a point of zero size and effectively infinite density. Physicists call this a singularity. The entire mass of a giant star's core, compressed into a region with no volume at all. Not small, not tiny. Zero. All that mass and no space for it to occupy. Now, be honest with yourself for a moment. That idea does not fully make sense. Infinite density. Zero size. Those are not numbers the human mind can truly hold, and that discomfort you feel is not a failure of understanding. It is the correct response. Even the equations feel it. When physicists run the mathematics of general relativity down to the singularity, the numbers stop behaving. They blow up to infinity. The theory, in effect, throws up its hands and says, "Beyond this point, I no longer know." This is one of the great unsolved problems in all of science. Our two most powerful descriptions of reality, general relativity, which governs the very large, and quantum mechanics, which governs the very small, both apply at the singularity at the same time. And they do not agree. They contradict each other. The singularity is precisely the place where our best physics collides with itself, and no one yet has the complete answer for what truly happens there. Sit with that. Not a mystery in the ordinary sense, not something we simply have not measured yet, but a place where knowledge itself reaches a genuine edge. A star lived and died to create the one location in the universe where science, for now, must admit it cannot see. And yet, strangely, we are not entirely blind. Because around that unknowable center, nature draws a line, a boundary that separates what we can know from what we can never reach. That boundary has a name, and crossing it is the most final act in the cosmos. Step over it, and you can never return. Not you, not light, not information, not anything. So what would it actually be like to approach that line? Imagine for a moment, that you fell toward one yourself. Around every black hole, at a certain distance from that crushed center, there is an invisible surface. You could not see it, touch it, or feel it as you crossed. There is no wall, no shimmer, no warning sign, and yet it is one of the most absolute boundaries in all of nature. Astronomers call it the event horizon, and it marks the point of no return. Here is what defines it. To escape the pull of any object, you have to travel faster than its escape velocity, the speed you would need to break free of its gravity. Leave Earth, and that speed is about 11 kilometers per second. But the closer you drift to a black hole, the higher that required speed climbs. At the event horizon, it reaches the ultimate limit, the speed of light itself. And since nothing in the universe can travel faster than light, nothing at that boundary can ever escape. Think carefully about what that includes. Not just spacecraft, not just people or planets or stars. Light itself, the fastest thing there is, cannot climb back out once it crosses that line. And that is the reason a black hole is black. It is not dark because it is empty. It is dark because it captures every ray of light that falls in and never lets a single one return to tell us what it saw. We see nothing because nothing is permitted to come back. So let us make it personal, the way curiosity demands. Imagine you drifted toward one. For a long time, nothing dramatic. You would fall, weightless and calm, the way an astronaut falls around the Earth. You might not even know the precise moment you crossed the horizon. There would be no jolt, no boundary you could feel. One instant you are in the universe we all share. The next you are somewhere from which no message, no signal, no cry for help can ever be sent back. And that is the quiet horror of the event horizon. It is not violent, it is not loud, it is simply final. A one-way door in the fabric of space, through which everything may enter and nothing may leave. Once you are inside, the outside universe is closed to you forever. And the outside universe, watching, will never truly see you cross. But do not mistake that calm approach for a peaceful journey. Because as you fall deeper, the forces waiting for you are anything but gentle. What happens to a human body as it falls toward the center is one of the most vivid and most disturbing consequences in all of physics. Scientists even gave it a name, almost playful and entirely accurate. And near that boundary, something happens to time itself that would make anyone watching you refuse to believe their own eyes. Let us confront it directly, because this is the moment the whole story has been leaning toward. The point where the abstract becomes physical, and gravity stops being an idea and becomes something that happens to a body. As you fall toward a black hole, feet first, gravity pulls on every part of you, but it does not pull evenly. Your feet, being closer to the center, are pulled harder than your head. On Earth, this difference is so tiny you never notice it. Near a black hole, it becomes monstrous. The pull on your feet grows so much stronger than the pull on your head that your body is stretched, lengthened, drawn out, pulled apart from end to end. Physicists gave this a name that is almost gentle for what it describes: spaghettification. You would be drawn into a long, thin stream of matter, stretched like a strand of pasta toward the dark. It is a grim image, and it is meant to be, because it makes the mathematics real. These are called tidal forces, the same family of forces by which the moon raises the tides in our oceans, only here amplified to a degree that shreds solid matter. What is a barely measurable difference on Earth becomes near a black hole, a force that no material, no bone, no atom-to-atom bond can withstand. Nature stretches you until you are no longer a shape at all. But the body is only half of it. Something even stranger happens to time. Einstein showed that gravity does not just pull on objects. It slows the flow of time itself. The stronger the gravity, the slower time runs. And near the event horizon of a black hole, gravity is so extreme that this effect becomes staggering. To you, falling in, your watch would tick perfectly normally. Your final seconds would feel like ordinary seconds. But to someone watching from a safe distance, something impossible unfolds. As you approach the horizon, they would see your fall slow down, and slow further still, until, from their point of view, you appear to freeze at the very edge, hanging there, your image dimming and reddening, never quite crossing. To you, the crossing is instant. To them, it takes forever. Two observers, one event, two utterly different truths. And both of them correct. That is not a trick or an illusion. That is how time genuinely behaves when gravity becomes this strong. Now, everything we have described so far came from the death of one enormous star. But here is where the universe surprises us again, because not every black hole is born this way, and some of them are so large that a single dying star could never explain them. Just when you think you understand what a black hole is, the picture grows far bigger. Set aside for a moment the single dying star. It is time to widen the lens, because black holes come in a range of sizes so vast that the ones at the extremes seem to belong to entirely different stories. The kind we have been following is called a stellar mass black hole. It forms exactly as we described. A massive star collapses, and what remains is typically a few times to a few dozen times the mass of our Sun, packed into a region only a few kilometers across. These are the most common. Our galaxy alone is thought to hold many millions of them, scattered through it like dark seeds, most of them silent, invisible, betraying their presence only by their gravity. But then there are the giants, and the giants change everything. At the centers of galaxies sit supermassive black holes, objects with the mass of millions, and in some cases billions of suns. Not a few times the Sun, billions. A single one of these can outweigh every star in a small galaxy. And here is the puzzle that keeps astronomers awake. No single dying star could ever produce something that enormous. So how they came to be, how they grew so vast, so early in the universe's history, remains one of the deep, open questions of modern astronomy. Between these two extremes lies a stranger, more elusive population, intermediate mass black holes, hundreds to many thousands of times the Sun's mass. For a long time, they were almost theoretical, suspected, but rarely caught in the act. They may be the missing link, the bridge between the stellar black holes, born from single stars, and the supermassive monsters anchoring entire galaxies. Every one that astronomers confirm helps fill in a story that is still being written. So the simple picture, black hole equals dead star, turns out to be only the first chapter. Yes, stars make black holes, but the universe has found other ways, on other scales, to create these regions of no return. From objects a few kilometers wide to titans larger than solar systems, they share the same essential nature, and yet span a range almost beyond comprehension. And one of those giants is not a distant abstraction at all. One of them is remarkably, unsettlingly close to home. Because at the very center of our own galaxy, the Milky Way, the band of light our ancestors gazed at for tens of thousands of years, there sits a supermassive black hole. And we have not only calculated it, we have actually seen it. Step outside on a truly dark night, far from any city, and look toward the constellation Sagittarius. Somewhere in that direction, buried behind thick clouds of dust and the crowded glow of countless stars, lies the heart of our galaxy. And at that heart is a monster. Its name is Sagittarius A star. It is a supermassive black hole with a mass of roughly 4 million suns, and it sits about 26,000 light-years from where you are standing. For decades, it was an inference, something we deduced from the way stars near the galactic center were behaving. Astronomers watch those stars whip around an invisible point at breathtaking speeds, following tight orbits around something they could not see. Only an object of tremendous mass, crammed into a tiny space, could fling stars around like that. The math pointed, unmistakably, to a black hole. The precision of that work is worth pausing on. Astronomers tracked individual stars for years, decades, watching them loop around the galactic center in orbits that could only be explained by 4 million solar masses, concentrated into a region smaller than our solar system. That patient, careful tracking of stellar motion earned a Nobel Prize in physics, a testament to how rigorously the invisible had been measured. We knew it was there long before we ever saw it, the way you can know a heavy object sits on a trampoline just by watching everything else roll toward the dip. And then, in 2022, the invisible was made visible. Using a network of radio telescopes spread across the entire planet, working together as if they were a single instrument the size of the Earth, astronomers captured an actual image of Sagittarius A star. Not a drawing, not an artist's impression, a real image, a dark central shadow, ringed by a glowing halo of superheated gas, bent into a circle by gravity so intense it warps the very path of light. Humanity had photographed the monster at the center of its own galaxy. Let that settle. This is not happening in some far-off, unreachable elsewhere. Every star you have ever seen, every constellation you learned as a child, the entire Milky Way, all of it slowly wheels around this one dark point. We are, in the largest sense, in orbit around it, right now, tonight. The abstract has become the local. The theoretical has become our own address in the universe. And it leaves us with one last question, perhaps the most profound of all. We have watched a black hole be born. We have fallen into one. We have found them scattered through the galaxy and enthroned at its center. But is a black hole truly forever? Or could it be that even these, the most unstoppable objects in existence, must someday come to an end? For most of the 20th century, the answer seemed obvious. A black hole only takes. It swallows matter, light, everything that strays too close, and it never gives anything back. Nothing escapes the event horizon. We have said it again and again. So by every reasonable expectation, a black hole should simply last forever, growing, waiting, eternal. And then one physicist looked closer and found that eternity had a crack in it. His name was Stephen Hawking, and what he discovered, drawing on the strange rules of quantum mechanics at the very edge of the event horizon, was astonishing. Black holes are not perfectly black after all. Through a subtle quantum process at that boundary, a black hole very slowly leaks energy away into space. We now call it Hawking radiation. Grain by grain, over time, a black hole gives back a faint trickle of what it seems to have taken forever. And if it radiates energy, then it must lose mass. And if it loses mass, then, impossibly, unthinkably, it must eventually evaporate. A black hole is not immortal. It is dying too, just as its parent star did, only across a stretch of time so vast it defies all meaning. For a black hole like Sagittarius A star, the evaporation would take not billions of years, not trillions, but a number of years with so many zeros that the universe as it now exists is barely a flicker by comparison. Slow beyond slow, but not never. Sit with the full shape of it. A giant star is born. It burns. It wars against gravity. It loses. It collapses. It explodes. And it leaves behind a region of no return, a thing that seems to defy the ordinary rules of birth and death. And yet, even that, in the end, fades. The universe, it appears, permits nothing to be truly eternal. Everything that begins, however impossibly, also ends. The black hole is not an exception to that law. It is its most patient expression. And so, we arrive back where we started, at a dying star and a countdown you could feel. But now, you know what that countdown was truly leading toward. Not an ending, but a transformation. Light into darkness, matter into mystery, and finally, across unfathomable time, darkness itself back into the faintest whisper of energy. That is the life cycle of the most extraordinary objects the universe has ever made. And you have just followed it, from the first flicker to the final fade. If this journey through the life and death of black holes gave you a new way of looking up at the night sky, then take a moment to subscribe to the channel. That is what allows these deep explorations to continue reaching you. Tap the like button because it genuinely helps this video find others who share the same sense of wonder. And I would like to leave you with a real question, so tell me in the comments. If you could send one probe into a black hole to answer a single mystery, knowing it could never come back, what would you most want to know? I will be reading your answers. Until the next journey into the dark, keep looking up.